Good morning, I'm Will Owens.
I'm Daniel Park.
I'm Andrew Heim.
I'm Daniel Tang.
And I'm Devin Sinkew, and today we'll be presenting a method for in-flight adjustment of wing dihedral with folding wings and tail.
Before we started on our goals for our project, we first identified two problems with modern aircraft. The first is the permanent wing geometry determined years and months ahead of aircraft production. This usually trades between efficiency, stability, and maneuverability, making sacrifices in one area to make benefits in another. Another problem we found was a large storage footprint. This has been a problem ever since World War II, where aircraft carriers have to carry many planes and there's not a lot of space, making it very dangerous to work.
So the two wing designs that we consider for this project were the dihedral angle and the flat wing design. So the dihedral angle is where both wings are slightly angled upward, and this causes a decrease in efficiency because the lift vectors are not perpendicular to the wing. So why would we want to use this angle? Well, it sacrifices efficiency for stability. So as seen in figure 1, when the plane rolls slightly to the right, it will have the right wing will become perpendicular with the lift vectors. And that will result in a higher lift on the right wing as opposed to the left wing. So this will create a self-correcting mechanism for the plane to roll towards its left side and realign with the center. The second wing design was the flat wing, as seen in figure 2. So because the wings are completely flat and horizontal, they will always have a perpendicular lift vector to the wing. And this causes an increased efficiency. However, it is not as stable because it doesn't have the same self-correcting mechanism as the dihedral. But it does have improved maneuverability. The dihedral angle, when trying to make complicated maneuvers and turns, the self-correcting mechanism will kind of go against that maneuver, making it less maneuverable, but the flat wing design does not have that.
So we came into this project with a number of goals. Our primary goal is to improve the flight characteristics on a situational basis. So depending on what kind of situation the aircraft is experiencing, it will change to adapt to that. And our secondary goal is to reduce the storage footprint of fixed wing aircraft. So what we were really trying to do here is to construct a functioning model radio-controlled plane that would solve these problems.
So as Andrew said, our primary goal was to be able to change flight characteristics at any time, which we chose to accomplish through an adjustable dihedral angle, which we accomplished through flexible wings. So at any point in flight, our aircraft could have optimal stability with the dihedral shape or optimal efficiency with a more flat wing shape. And to accomplish our secondary goal, which is a smaller storage footprint, we chose to accomplish this through a folding wing and tail mechanism.
So the most important part of any plane is the wing, because that is what allows the plane to fly. So when thinking of what kind of wing design we would think about, we did some research, and we came across the NACA 2412, which is shown in figure 3. So why did we choose this airfoil design? Well, we intend to fly our plane between the angles of around 0 to 10 degrees, and as shown in figure 4, the coefficient of lift is significantly greater than the coefficient of drag. For example, at around 6 degrees, the coefficient of lift is around 50 times greater than the coefficient of drag. And this is important because lift is what keeps our plane in the air, and if that is significantly greater than the drag slowing it down, our plane will be able to be more stable.
So as Devin mentioned earlier, our plane has an adjustable dihedral mechanism. To enable this, instead of using hinges, we use a flexible wing design. Though there are hinges on our plane, they are only used for the folding wing and tail. So by using home insulation foam for the material, we create a strong, very flexible wing that has a low chance of breakage. So we actually have a winch central to the fuselage that pulls on either tip of the wing, inwards and upwards, creating the dihedral shape that's wanted.
As Will said, we have a single winch that controls both of the wings and functions for two purposes. When locked outward, it functions to put the dihedral flex in the wings, and when unlocked, it allows the wings to fold up for better storage. We were also going to implement the same locking and winch mechanism in the tail, but due to time constraints, we were unable to finish this process in time for our flight test.
So elaborating on that, the mechanism for our folding wings and tail is really quite simple. It's simply the tail and wings fold at the hinge because there's fishing line attached to the tips of the wings and tail, connecting back to the winches. So when the winch turns, the wings fold up.
So to secure each wing in flight, we use a system of 2 composite spring-loaded pins. So in flight, these pins can push out into each respective wing, locking all motion. However, once it's landed, a servo motor can retract the pins so that the wings can fold up along with the tail. Here we have an exploded assembly that'll show each part and how it fits together. You can see the motion of the wings. The servos are removed along with the tail. Here's the motor and propeller assembly. And finally, the entire wing assembly being removed. So you can see here the locking pins on the bottom, the winch right up top, and each wing right in the middle in purple. So to optimize our wing design, we used a finite element analysis. This is basically like a digital stress test of the wing, and it enables you to simulate loads that you might see in flight. Here you can see the loads of drawing the wing into a polyhedral shape. So we have one on either side from the winch. In orange, you can see areas of higher stress where the wing might break. And to create a stronger wing, we reinforced it in only these higher stress areas with balsa spars.
In addition to the computer analysis, we also performed a stress test on the physical wing itself. And we did this by attaching a force gauge to the edge of the wing, which was clamped to the table as seen in figure 12. The force gauge allowed us to apply certain amounts of force onto the wing, and then we used that to measure the displacement from its original position without any force being applied on it. We then used that data and plotted it on a graph as shown in figure 13. The blue line represents the displacement of the wing without the spar, and the red line represents the displacement of the wing with the spar. The data shows that there's significantly less displacement when the spar is in the wing, and this is important because it adds rigidity. If there is no spar in the wing, our wing would be too flexible and bend during flight, causing a loss in lift. However, the rigidity provided by the spar allows us to maintain constant lift throughout flight.
Before we started construction, we realized some potential issues. First of which, mechanical malfunction. Our mechanisms could fail during flight. If the pins came out, the wings would flop around and we'd fall out of the sky. If the tail came undone, we'd flop around and fall out of the sky. The control surfaces also get a little bit interrupted when we flex the wings, which could cause control problems. But also other structural issues, as Daniel mentioned earlier, like the flexible wings being too flexible.
Next, we moved on to our construction step. So as you can see here in figure 14, we cut out little wooden guides to enable us to get our exact airfoil shape with the hot wire cutter on the foam insulation. And in figure 15, you can see us attaching our control surfaces with servos and air horns connected by piano wire. So when the servos are moved, they enable the control surfaces to move up and down. And in figure 16, you can see our locking mechanism, which has the fuselage removed just for the aspects of view. But you can see the servo with a winch system connected to fishing line that pulls the carbon fiber pins into the center part of the wing. And in figure 17, you can see our main winch system that we talked about earlier that flexes and folds up the main wings.
So the electronics of the plane. Here you can see in figure 18 a general layout for most RC planes. You first have the battery, which obviously supplies power for both the motor, the receiver, and the servos. On the left of that, there's the electronic speed control, which basically controls how much power is sent to the motor and to the receiver. The motor itself simply spins the propeller, provides our lift, or our thrust actually. pushes us forward. The receiver takes radio signals from a transmitter or the controller on the ground and converts them to electrical signals to send to the servos and control how fast the motor spins.
So fortunately for us, all of our mechanisms function just as they were designed to. This is including the dihedral adjustment mechanism, the locking mechanism, as well as the folding wings and tail. So in figure 19, you'll see the dihedral mechanism in action. So this is obviously when the pins are locked, so the hinges cannot move. So when the winch spins, the wings flex upwards. This is in figure 20, you can see our locking mechanism. So when the pins are out, as they are now, the hinges cannot move, which enables the polyhedral mechanism. And when they go all the way back in, which you'll see in just a moment, it is unlocked so the hinges can move and the plane can fold. And just as I just said, this is the mechanism for our folding wings. So obviously the plane is unlocked and the wings can fold all the way up. So the folding tail, as Andrew previously said, we did not have enough time to actually implement this in our flight test. So basically this video is just showing that where we plan to put the servo, it did have enough torque to fully lift the tail. But for the flight test, we had to glue it back down.
So here's our flight test. It was a little bit rainy and a little bit cloudy, but thankfully Rob, our test pilot, still did a wonderful job flying our plane.
So you can see our collapsible wing functioned exactly as we wanted it to. Right in flight, perfect. So though we did end in a crash here, all of our mechanisms did function as expected on the ground and in air before the crash. In fact, none of the mechanisms were the cause of the crash, and on top of that, after the crash, none of the mechanisms that we designed even broke. So we consider this a successful proof of concept for our design and mechanisms.
So as was said, our flight test did result in a crash, which is unfortunate, but all the mechanisms we designed worked perfectly, and that we hope for the future that some of our mechanisms, especially the changing wing structure, can be implemented on the full scale. And we hope that this could help improve some of the problems faced in the flight industry. This could include improving safety, optimizing maneuverability, and also improving fuel efficiency. So even though more work still needs to be done to perfect these mechanisms, we consider this a successful proof of concept.
We'd like to acknowledge our project mentor, Ryan Mulroney, our test pilot, Robert Panko, Brian Lai, our research coordinator, Nick Ferrero, our head counselor, Dean Rosen, our program director, Dean Antoine, our associate program director, Rutgers University, Rutgers School of Engineering, the state of New Jersey, corporate sponsors, and GSET alumni.
I'd like to open the floor to any questions.
Yes.
What would the best practically, what would the best way to see this innovation being used?
So we actually see a bunch of applications for the folding wing, which wasn't our novel design. So for example, the Corsair plane in the Navy had folding wings to save space, and actually a lot of modern Navy planes have that same design. As for the adjustable dihedral, we see that in environments where you might want to trade off maneuverability and efficiency and stability all in real time. So in flight, you can actually change these properties without much disturbance to the aircraft. So you might think there's planes that fly through hurricanes, right? And they have very rapidly changing conditions, but in most modern aircraft, you can't change the shape of the wing in flight. So you're stuck with what you have, but in this, you can change all of those properties. Yes?
So if you were to do the project again, what would you do differently next time?
We would implement better construction techniques to make sure that our plane does not fall apart midair.
It was actually due to a faulty hot glue joint. Yeah, that was my bad. Yes.
For your simple aircraft, do you have a landing structure so that it can prove it, keep it from the crashing?
Can you repeat the
Do you
question?
have any landing structure on the bottom? So that
No, we don't.
Not for this.
So
No, not this one.
we did originally design one, but we decided that we'd be flying in grass fields where there was not much risk of damage to the aircraft. In fact, probably the bigger concern was just hitting it nose first at 30 miles an hour. But yeah.
So it's like a soft landing.
In future aircraft, we might implement